Hello. First of all, thank you much, Singh, for inviting me to be the plenary speaker. And it is something I would like to talk about, something that I have been thinking about and working on for about a year at UCSD and with certain companies. And you are going to see some intriguing results, I would say. So. At the beginning, let me say what we are doing at the center. We are doing lots and lots of arrays, wideband arrays, dual frequency arrays, RIS, and all of the stuff, lots of wideband circuits, and we are thinking about AI and how to make a difference in circuits. The first thing is I want to show you some of the work funded by the center. This is a dual frequency randomized nested array to work at 7 to 8.5 gigahertz, and in this case, 11.6 to 14.4 from the same aperture, so that you can. I mean, that was done when we thought 6G was going to be 13, 14. Of course, we can do this when if they move the frequency to 15, 17, and it worked really, really well. You could see the bandwidth of this. This is rather than having a 7 gigahertz array and a 14 gigahertz array, you can nest them together in the same aperture. Very nice for Nokia and Ericsson and so on. And both of them scan very nicely. And of course, you can do hybrid beamforming and subcells and break them into elevation and azimuth and so on and so forth. But this is just to show that it works well. In this case, we built our own beamformer chips using SiGe from Tower Jazz. The other one is a dual polarized 7 to 8.5 gigahertz dual slanted polarized reflect array with less than 3 dB loss. We have now arrived to be able to make RISs. And look at this, how large it is, 26 by 26 centimeters of active area, scanning plus or minus 60 degrees in all planes. This entire thing consumes 2 watts. 2 watts. I mean, it's really the microcontrollers and the leakage and this and that. SP4T based from P-Semi, the ones are donated by P-Semi. Phenomenal performance, less than 3 dB loss. When you have phased arrays that are less than 3 dB loss, you might want to say, well, maybe I do not make a phased array, active phased array anymore. I just have a focal plane feed, and I just increase the power by 3 dB. And that's it. And rather than distribute things, and just use passive switches everywhere. Dual pole, half a lambda grid. You put 4 of them together, you get half a meter by half a meter RIS for less than 8 watts or something like that. And you could see here the cross pole, 20 dB, 25 dB cross pole. It's dual polarized. And you could see how if we put a wave at an angle of minus 20, how we can scan it to minus 10 and 0 and 10 and 20 and 30. Really works very, very well. And we are delivering this. If you are a CWC member and you say, hey, Gabriel, ship me 4 of these, ship me 10 of these, we'll be happy to do that. We'll just charge you for the BOM and a little bit of students and some alcohol, and that will be fine. And of course, thank you, P-Semi, for making this phenomenal switch. Also, we are doing here 13 to 15 gigahertz, randomized just to reduce the number of elements, but keep the beam width. Randomized arrays, again, dual pole. And again, when we thought 6G was going to be 13 to 15, now people are saying 15 to 17, but it's the same thing. Here it is, you're using ADI switches. Again, phenomenal SP4Ts, the 5040, 5050 series, all of them are FSOI switches. And again, you could see performance plus or minus 60 degrees scanning. This is with a focal plane, again, less than 3 dB loss. So, let's say we are doing really good work, and we are delivering these arrays to, many, many different companies who are interested. I literally can deliver a 1x1 meter array if you want to. Literally at these frequencies. So now let's talk about AI. So first, before I dissed AI a little bit and so on, let me do a disclaimer. It's phenomenal. It has replaced a lot of jobs, especially in the software. It has done unbelievable things in software, code writing, code, and so on, and coding, and in data analysis, and large data sets, and languages, and writing, and law, and videos, and stories, and movies, and blah, blah, and so on. But has it done anything yet in RF circuit design? So let us take an example of a power amplifier design. Really, a PA design is basically taking a small input, and turning it into a big output. So this big output, look at this. This is Peter Esbeck there, okay? That is the top predator, Peter Esbeck. That's how he basically got married and fathered so many children. That's him. That's Peter Esbeck, basically. Now, in the PA, there are specifications. And the specifications is like, I want a gain, output power, I want high PAE, this is my operating frequency range, harmonic suppression, blah, 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 and so on. So the first thing we do is we say, okay, we're going to choose a technology. Let's say I choose a WIN gas 5-volt technology that gives me 3 watts per millimeter. WIN uses a load pull station, like this one. And load pulls the PA and says, this is the typical impedances you want to show, like we do with an LNA, and you say, this is the optimum noise figure. They do the same thing with the PA. And this PA delivers 3 watts per millimeter. This technology delivers 3 watts per millimeter. So if I ask you for a 1-watt device, you have no choice. If you design a PA with 0.5 millimeter device, you will never get 1 watt. If you design a PA that is 2 millimeter periphery, you are very inefficient. You have only one choice, and it has to be a 1 millimeter device if it is 3 watts per millimeter, let's say 1.16 and so on. Because 3 times, it has to be exactly that. Now, okay, we can change plus or minus 5%, but the device is highly deterministic. Now, SiGe and CMOS, you would say, okay, this is my voltage swing. I need to make my device that wide in order to handle the current, and it very quickly limits you into a very small device. And you have no choice. If you choose a 0.5 millimeter device, I will shoot you. If you choose a 2 millimeter device, I will fire you and then shoot you. You have no choice. It's a highly, highly constrained set of devices that you can choose. That's it. And let's just go back. This is a big SiGe device. This is a big CMOS device, and these are gas fingers and so on. Let's continue on that. After you do this, your output and input impedances are known. You have no choice. That is, you've chosen your device. Your impedances are known. You basically put it in Genesis, ADS Genesis. ADS has done Keysight a phenomenal software with ADS and Genesis. And you synthesize an input matching network and an output matching network that is going to meet your circuit parameters. This is your bandwidth. This is your load pull impedance. This is your input impedance. That's it. It is actually, again, a highly deterministic design. And it's going to give you a network that's going to be, of course, lossless and made of L's and C's in different form and configurations and transformers and this and that and so on. And after that, you are going to sit down and lay it out in a compact form. So very quickly, you realize that circuit design is not heuristic and not a large language model. It is actually extremely, extremely deterministic. It is, for PAs, it's a very small transistor sizes that you are allowed. For LNAs, it's also, well, instead of doing a 40 micron device or 80 micron device in SiGe, you do a 6 micron device because it's an LNA. And we'll get to LNAs. It's a small range of matching network. And again, ADS and Genesis are phenomenal, and they will do this for you. And so where is the trick here? The trick is to make these networks, to make these matching networks, to make these down at the bottom in the most compact form, in the smallest and most compact form, and simulate them with all their parasitics. That's the trick here. Now, The point is that accurate EM simulations takes a lot of time. That's the problem. Until now, we have not figured it out. It takes accurate EM simulations. And also, let's go back a little bit. IBM, global IBM, before they sold to Global Foundry and so on, had a design kit. And it was in the 2005, 2010. And they said, no, 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 no. You Qualcomm, you Broadcom, you Ericsson, you Nokia, ADI, TI, don't worry about it. I'm going to design your inductor. And these are 40 inductor values. I'm going to design your capacitors. These are 40 capacitor values. I'm going to design everything for you, fully EM model them, and put them together. And then you go in and you put them together, plop, 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 plop. Effectively, they were designing these separate components and giving you a very large library. And you know, the industry started using them a little bit at 3 gigahertz and 5 gigahertz with 5PA, SIGI 5PA and 7PA and so on. These are the processes. But then, very quickly we said, why are we doing this? It's just too large. We want to compact them and compact them and compact them and make something much, much smaller. And then we quickly abandoned the IBM approach and we started designing things that are very compact. Extremely compact. I mean, this is an example of compactness. Now, this is an old chip from Qualcomm. And you could see all the inductors and all the lines and all the bumps and the vias, like the flat portions are bumps that have been removed and so on. And this is 28 nanometer, which I pulled out from the web and I fix it and things like that. I don't dare showing you 7 nanometer because they will shoot me. And I don't, but 14 nanometers, we could show you 14 nanometers. That's an old one. But you could see how many inductors there are. And there are bumps next to them. And there are more inductors next to them. And there is so many things. And look at this here. This here. Like, they have an inductor here. And then they want to put a bump next to it. They have 2, 3, 4, 5 inductors. They want to put a bump next to it. The point is you realize that there are infinite solutions. Infinite solutions. And you would say, at the beginning, I was saying, well, I'm going to do better than IBM. I'm going to take these inductors and now do the coupling between them. The other thing with IBM is that IBM said, put them at a certain distance away so that I don't take any mutual coupling between them, so that you can use them. But here you have to sit down and for example, co-simulate these together. You have to sit down and co-simulate these together. And then you have to simulate, oh, there is a bump here, and this bump is like 100 micron big, and it is big, and it is changing your inductance. And you realize that it is infinite number of permutations. You cannot make a matrix anymore to say, oh, I'm going to make a matrix of best possible scenarios and pull it from it, because everybody wants to compact as much as possible and wants to lay out chips that are stuff, and then wants to put bumps next to them. So after you simulate them and you want to put bumps next to them here, you have to re-simulate again because you actually definitely change the value of the inductance. This is not easy stuff. Now, I'll take you, for example, onto an LNA design in 4 stages. Now, this is single-ended because you wanted to make it low power. So again, first, which, by the way, let me go back here, even simulating the device and how we connected from M1 for a large power amplifier device and how we connected all through the metal stack, this alone is also a full EM simulation. Otherwise, you shift the frequency, and it will not work, and the parasitics will not work. So this is another example of an LNA, 3-stage LNA, all common source, and 45 SOI. And now it is a 3-stage LNA, and Global Foundry says, if you want a low noise amplifier, you have to bias at 0.1 to 0.2 milliamps per micrometer. That's it. If you sit down and you bias at 1 milliamp, not only are you consuming more power, or at half a milliamp, you're also not giving me the lowest noise. So I will shoot you, I will fire you, and I will shoot you. I mean, what I am trying to tell you that anything you build in RF is a highly constrained set. LNAs, you know exactly the bias. You know exactly the size. PAs, you know exactly the size. Now is the worst problem because this is single-ended. You have to model the input bias. input the ground inductance, and you have to model the transition in and out inductance, and you have to model the VDD inductance, and you have to model all of this together. And that's how I decided to lay it out, and somebody else decided to lay it out differently. And you want to make the smallest and the smallest. So you flip it, you model everything, and look at this. This is a SATCOM PA at 18, 19 gigahertz. It works very well, and it has simulation and measurements are reasonable, and it works well. But things are really complex. This is another 5G vector modulator, which using these, for example, double-nested transformers. And you sit down and you model them and you pay attention, and you have two of them here and there, and you model them, and still you end up, just because you missed a little bit on modeling, you end up with like 4 or 5 dB loss here at 24 gigahertz. Now, I mean, I'm sure in RF and in PAs, you know the rule. You kill your grandma for a dB, and you divorce your wife for 3 dB. So basically now, you have forced me to kill my grandma and to divorce my wife at the same time, just because you did not have enough resources to simulate this complex structure. So you quickly realize that it is AI. It's not about device choice. It's not about large language models. It's about very accurate EM simulations. That's it. That's what it is. Now, of course, you know, and I tell a story from Ericsson. I was once meeting there. If you build 100 million PAs like a Qualcomm, and for handsets, and Skyworks, and Qorvo, and then you go measure them, you of course use AI to do full analysis of statistics and to figure out which is the best bias point to get me for this process, and what is that, and what's that. And I can tell you, Ericsson has been doing it, I would say, for 10 years. 7, 8 years ago, I heard one of the most beautiful things from an Ericsson engineer. He said, we do, of course, digital predistortion and all of these, you know, coefficients for base stations, PAs. And we buy, let's say we are buying from Qorvo PAs, Mitsubishi, Qorvo, and so on. We can detect the trap density by seeing in our analysis how much coefficients we have in our predistortion. And we literally call back the time and so on. We literally call Qorvo or Mitsubishi, say, hey, fix your process because your trap density is increasing and it is causing me more coefficients to linearize your amplifier. I mean, this is large data models, and that is where you can use it. But you can't use it for design. Design is highly deterministic. And literally, they go back and feed to them. Say, how did you know? How did you know? Blah, blah. I say, I know because, I'm actually linearizing your transistor, and I know your trap density, and I know the time it takes, and I know how, and I'm measuring 100,000 of them, so I know. Go fix it, literally. That's where it happens, in the measurements, but not in the design. Now, we go back. So some people said, what I am going to do is I am going to replace your matching network with this EM-generated thing. And in my opinion, it's a good first step. But until now, the results are highly underwhelming. Highly, highly underwhelming to the point of being a joke. The point is the fundamental theorem of electromagnetics says, if we are using the same metal, if we are using the same volume, no one can do better than the other. That could be the Q theorem, or the Foster theorem, or the Bode-Fano matching theorem, all of them. There are many embodiments of the theorem. It's that we are limited by the Q of the network, and the Q of the environment, and the volume, and that's it. We'll all arrive to the same thing. Thus the single solution that Genesis will give you for a multi-port matching network. Kind of. That's the solution, and there is no other. Because we are in differential linear equations, and once you find the solution, it's a unique solution, effectively. I mean, welcome to differential equations. So they said, no. I'm gonna go make these solutions. The point is that if you put a good engineer, then you will be able to make much smaller matching networks than what is here. The point is, so I summarize it by this way. It is replacing a bad engineer with another bad engineer. Actually, there is a company, a large RFIC company, that hired me as a consultant. And they said, I'm so afraid of this technology, what we're going to do. We went and looked at every filter, every network, everything that is published by Princeton and USC and everyone doing it. And if we actually put a good engineer on it, we reduce the area. Because they're nothing, they're like 2-pole, 2-0 circuits. They're a simple filter, a simple matching network. We went and we put a good engineer on it, and within 1 hour or 2 hours or less than a day, we reduced the area by a factor of 3. We reduced the area by a factor of 3. Are you kidding? Kamal Sahota, senior VP, will kill me. I remember once a few years ago, and I said, come on, I want to try this tunable network thing, and I want 2 square millimeter on the chip. And he started laughing at me. He started laughing. I think he laughed for a week. He laughed for a week because I asked for 2 square millimeters, to try something on a chip. Yeah, he said, are you kidding? You're not going to get 5 microns, basically. Forget about it. So we went and looked at everything published. And everything we could make 3 times smaller, 5 times, just by putting a good engineer on it. That's it. That's it. I mean, the point is that at the end, it's replay. And that's why I actually fault my colleagues here. And I say, they publish these things without rigor or a very strict comparison table by saying, okay, this is what my AI can do. Now, let me put a good engineer on it and see what they can do, and let me compare. They don't have it in the papers. They say, that's what my AI can do, and I am the king of the world, and that's fantastic, and look how everybody should be excited about it. No, I am not excited about bad engineering, period. I'm only excited about great engineering. Yeah, and this company said, Gabriel, whatever you charge us 10 times more, because you just saved us millions and tens of millions of dollars. Yes? Oh, I did. Yeah, no, I'm not going to say, but, I am no person that I should consider shy, basically. Yes. I will tell you what is a great filter. A great filter is something that we have done and published in my group of a 4-pole, 4-0 filter with dual coupling and triple coupling, and all of this done in ADS, Genesis, HFSS, in an area of 0.07 millimeters squared, in having a passband from 4-pole 4-0, having a passband from 24 to 41 gigahertz in less than a dB loss in 45 SOI. That is a reference. That is something that a PhD can do and a great engineer can do. And that is something where AI is years and years away, because it still does not have the intuition, and it does not have the fast EM capabilities. Because every time you EM, you have to wait half an hour and so on. It does not have the fast EM capabilities in order to get into a 10,000 loop iteration to get there. Another one is, look at this, a tertiary 0.39 millimeter square done by Omar Al-Assar. Well, actually, yeah, this one, Li Gao, who went to MediaTek, this one, Omar Al-Assar, who went to Apple. And tuning from 8 to 16 gigahertz with unbelievably low phase noise. Again, this is something that cannot be done by AI. This is something that is very, very, very hard to do. Another thing which is close to my heart is, look at this. This is, from extreme waves, a radar. Now, look at the size. It looks big, but it's only 40 centimeters. It's that large, 40 centimeters. By only 15 centimeters, that large. And a depth of only 6 centimeters. Radiates kilowatts of pulses. Can detect a mouse at 50 kilometers, the RCS of a mouse at 50 kilometers. That is, and wakes up, turns on, and sends kilowatts in unbelievably short time. I'm not going to tell you how much the time. I'm not going to tell you the frequency. I'm not going to tell you, how much power it radiates. That is great engineering. This is where you make your countries great, is when you're able to do something and find a UAV at 50 kilometers, and then without it even knowing that you found it, and plot it and destroy it without even knowing that it has been detected. And I can tell you that this is sold, let's say, many base stations of Ericsson or Nokia, and that will be the price of one unit. I mean, that is like pinnacle of engineering. So that is my philosophy, is that AI is going to replace below average engineers. And but everybody is basically like this. It's going to replace bad engineers with bad engineers. That's great. That's fantastic. Because we really don't want these bad engineers in our gene pool anyway. I mean, let them go do acting and other things and gardening and taking care of people and being nice. But if you want to build the next Qualcomm, if you want to build the next Apple, if you want to build the next Nokia and next AMD, you want the best engineers. You want to train the best engineers. You want to build things that are very complex. But yes, if you want to do SPI drivers, clock recovery circuits, simple, not 200 gigabit per second, small microcontrollers, small things. I was at a big company in Texas. I don't know which one it is, but it's a big company in Texas. And yeah, I mean, they have 10,000 parts that are simple SPI driver and this and LDO and level shifter and this and that. Yeah, of course AI will replace all of these engineers. And all what they do is they port them from this to this process to that process. Oh, there's a cheaper process in Singapore, let's port them there. There's a cheaper process coming up in India, let's port them there. Of course, AI will do this very well. But can AI do something like this, which requires incredible level of engineering? Can AI do something like that? Well, first of all, just to do this require immense amount of EM simulations. Very accurate EM simulations. So yeah, but I agree. I agree with Misha. I agree with everybody. I mean, if we replace half of the population, then we have a huge problem. What do we do with half of the population? I mean, by everything is a standard distribution. You have excellent people and you have not so excellent, but they are good people. They are nice people. You want them in there. They are beautiful neighbors. They are fantastic, soccer people and so on. What do you do with them? If AI can replace all of them, what do you do with them, as is happening with software? I mean, basically, AI getting into software is telling us one thing, that most of software is easy. But most of hardware is very hard, basically. I mean, that's an indication. But really, what my job is as a teacher is to train students who are going to build the next Broadcom, the next Qualcomm, the next Ericsson. That's my job as a teacher. My job as a teacher is not to deliver below average or average students. My job as a teacher is to be able to deliver students who build something like this, and students who build something like that, students who build a PNAX that works at 200 gigabits per second or 200 gigahertz. That's what my job is. That's what most companies are. The last thing I want to say is, what can AI really do well? AI can solve phenomenal circuits like that. Now, this is a kind of time domain circuit. I close a switch, and it's time domain circuit. It is second, third order differential equations, and so on and so forth. This is an op-amp. But it takes me 4 to 6 months of training at the sophomore level to teach a student how to do it. But students are no more doing it. Since high school, all what students are doing is they just take these, put them in AI, and they get the solution. But then you go to Confucius, you go to Buddha, you go to Socrates, you go to Plato, you go to Seneca, you go to every culture in the world. And there is no learning without suffering. There is no learning without thinking. That's the only way to learn, is that you have to suffer and learn and suffer and learn to such a degree that the way I call education is sophomore is suffer more. Yes. Okay. That's what, that's where the learning will happen, is suffer more. Exactly. And there is no more suffering. The results are there. I mean, one of you called me and they said, we used to interview 4 or 5 students to get a job offer, to give a job. Now we're interviewing 12 to 15 because no one can solve a problem. No one can think, no one can solve a problem. And we at UCSD, I can tell you, are taking a very hard stance on this, extremely hard stance. I failed 25% of my senior graduating class. And in the sophomore year, we are failing 40 to 50% of our students. Because if they can't do the final exam without computers, they should not be engineers, period. Period. And we are taking a very hard stance on that. And so my conclusion now is, until now, I am not impressed by AI for RF circuit design. Now, I am specifically saying RF circuit design because accurate RF circuit designs require, first of all, as I said, it's very deterministic. And a lot of the work is actually on accurate EM modeling. And we have not yet solved the bottleneck of 100 to 1,000 times faster EM modeling. Accurate, faster EM modeling. We have solved the bottleneck of little EM modeling, like the circuits you see from Princeton and so on and so forth, but accurate and very tight and compact, so that you are not on the left side of the Gaussian curve, but you are on the right side of the Gaussian curve. We have not solved it. Yes. And I am actually, now, do we need to fund it? Of course, yes. I am the father of RF MEMS, and I was funded for 20 years, and the first 5 years, it was a completely disaster technology. And it took 20 years until it blossomed, and now we use it everywhere. So do we need to fund it? Yes. But please, let's be honest about it. They are not honest about it. Let's not blow it out of proportion. Anything that's published today, I can do it 3 times smaller, 5 times smaller in certain cases, in few minutes in certain cases. And I believe, and this is my famous last words, that well-trained students from great engineering schools will be successful, will lead companies, and will build the next generation of products and the next generation of companies. And to finish with this, I will give you other famous last words that for you to ponder, basically. Hopefully mine will not be part of these. Okay, thank you.